Here is a version of the Cauchy integral formula on an annulus. So assume f is analytic on this annulus. So all z's with modulus between little r and big R as we had before. And now we're just going to take an R1 and R2 in between little r and big R. And then we get a formula for f of z when modulus of z is between these two values using complex line integrals on circles that we've already studied. And so you get a term which looks just like the Cauchy integral formula on a circle that we've seen, but this is along the outer circle. So we have this term, and then we subtract a similar formula on the inner circle. So we have big R here, little r here. We have a couple helper radii here. I don't know if I should draw them all in, but here we'll have R1 and R2. And we can evaluate the function using a formula very similar to the disk case. And you should think through that if f is actually analytic on the disk of radius r, you can think about why this integral actually will give 0, and you do get the usual Cauchy integral formula on a circle that we've learned. To prove this, we have an easy lemma closely related to a lemma that we had to prove the Cauchy integral formula on a circle, which related to this difference quotient function. So if f is analytic on a domain U, and then I fix a z0 in U, I'm going to define this function g, which is given by this difference quotient when z is not equal to z0, but then it's equal to f prime of z0 when z is z0. And the lemma just says this defines an analytic function on U. You could actually do even better. You could write something out like f of z minus f of w over z minus w when z and w are different, and the derivative when they're the same. And this function you could write as a double power series in z and w. We don't need that here, but you could do it. So the proof is pretty quick. Let's put them side by side. Okay, so this function g, if I look at it at z's not equal to z0, it's evidently analytic just because there's no problem with the denominator, and the numerator is analytic too, so no big deal. At z0, though, we want to show that g is analytic around, on a disk centered at z0, and that's just a matter of writing out f's power series, and we can write that as f of z0, f prime of z0 times z minus z0, and then higher order terms, and then compute g in terms of this power series near z0. And when you do that, this operation of the difference quotient just kind of shifts these terms to the left and cuts down the degree of the monomials here. You can go through it to see it. Let's see, on the top we subtract f of z0 to the other side and then divide by a z minus z0 to cancel these. And so you end up with exactly this formula for g when near z0, when z is not equal to z0, but it agrees with the definition when z equals z0 because we get f prime of z0. And this is a power series centered at z0 that converges, so g is analytic at z0. No big deal. So this lemma shows this difference quotient defines an analytic function. Okay, we can use this to prove the Cauchy integral formula here. Let's try to put the stuff together. Okay, let's prove the Cauchy integral formula on an annulus. So let's assume all of this set up in the theorem, fix z naught in the annulus, and define g as we did in the lemma as this difference quotient. Now we're going to consider these complex line integrals on circles. So I've written it as modulus of w equals s. That just means the circle of radius s centered at 0. And when you write this out in terms of parametrizing the circle, it just becomes this integral from 0 to 2 pi of g of s e to the I theta s e to the I theta d theta over 2 pi. But we've already seen that when g is analytic on an annulus, we had a lemma in our proof of the Cauchy integral formula on circles that this is constant with respect to s. So that's just what I've written here. And so let's write out what exactly that means. So I'll put in these two R1 and R2, squeeze them in between modulus of Z naught and little r and big R, and just use the fact that this will be the same at R1 and R2. So at R1 I get this, and at R2 I get this. I've put in the difference quotient formula here, and since modulus of w is R1, I'm not going to ever have w equal to z naught, so I don't have to put in the case in this piecewise defined function here where I get the derivative, so everything checks out in that respect. And now let's expand this side, or break it up into two pieces. So we have this piece, which is part of what we want in our formula. And then you have this other piece with f of z naught that I can pull out front, and I just have this integral of dw over w minus z naught, and 2 pi I in there, of course. And you can do the same breaking up for the integral on the circle of radius r2. So I've broken it up in the same way. And now I just need to figure out what these two integrals here are. So let's think about it. Right here, let's see, z naught has modulus bigger than r1. So the function here that we're integrating, this is analytic in the disk of radius r1. And we can apply the Cauchy integral formula on circles to this. So how can we do that? Well, you can actually see that the integral is 0 as follows, and maybe this should have been also stated as a corollary, but if I'm doing this on the circle of radius r1, I can throw in a w and divide by a w, and now this part is still analytic on the disk of radius r1, but now putting this w in here makes it look like the Cauchy integral formula on a circle where we're evaluating a function at 0. But if you evaluate this function at w equals 0, you're going to get 0 because the w up here. So this integral is 0. So all this part goes away. But this other one, where I'm integrating on the circle of radius 2, well, you can apply the Cauchy integral formula on a circle here. You can think of 1 as your function, and we're dividing by w minus z naught, and we'd evaluate this function 1 at z naught to get just 1. So this part just becomes 1. And if you stare at this formula, we're going to get f of z naught is the right thing, as in the formula we're trying to prove. Okay, now let's apply this to prove that analytic functions on annuli have Laurent series.